In this video, we're going to get into the simplest mechanism of the reaction of alkenes. This is sort of the base mechanism that you must absolutely fully understand before we can do any other building upon this. And so the idea is you take a look at a double bond system like that, and you should really think of it as having a pair of electrons. In other words, any double bond is inherently nucleophilic. The double bond itself is simply an orbital that contains a lone pair in some sense. Sure, that pair of electrons is shared between the two carbons, but it can act as though it's a nucleophile, as a pair of electrons that can simply react with something else. So your double bond is always a nucleophile, a relatively weak nucleophile, but a nucleophile nonetheless. So as long as you have some sufficiently electrophilic reagent above the arrow, especially an electrophilic end of a reagent above the arrow, then a productive reaction can happen. HCl is a pair of reagents in some sense. It's an X and a Y. It's an electrophilic end and a nucleophilic end. The Cl is not nucleophilic at the moment, but can easily become one as long as it is attacked by a separate pair of electrons. Again, the idea here is that the electrophilic end will then cause the chloride to leave. Once the chloride has left, then it is a nucleophile and can add back in. So you really should think of HCl as being maybe an XY pair or possibly an electrophile bound with a nucleophile. This electrophile-nucleophile pairing is the way you really want to think about it. And the electrophile will always end up binding first, mechanistically, usually, and then the nucleophile will bind second, and that gives rise to the observed regiochemistry. You will almost always get what we call the Markovnikov product. And so what I've drawn is the example of a Markovnikov product, which is to say you form a carbocation with the plus at the most stable possible position. Okay, so let's get into the actual mechanism here. So I've already indicated in some sense how this is supposed to go. The double bond attacks the H, which then leads to a choice. And so now let me redraw this initial attack with two different colors to give you two different options. This is the first and only time that I'm going to draw things out in a relatively silly way. But I have a pair of electrons here, and it could either slosh to one side or slosh to the other before it goes off and make a bond. Said another way, there's a pair of electrons contained between these two carbons. Those electrons are shared between those two carbons. Either carbon could be the one that goes ahead and makes a bond to the H. So the way to think about it possibly is maybe these electrons slosh to the one side first before they go off and make a bond. Or it's also possible that these electrons would instead slosh to the other side before they go and make a bond. The reason why I'm pointing this out is because it leads to two potentially very different products, and we should consider both of them. So I'm going to draw out the red one first. The idea is that if the double bond sloshes to the right first and then makes a bond to the H, then this carbon is the one that makes the bond to the H, which means that the cation will be left over right there. There is an implicit hydrogen drawn there. I have now drawn it explicitly. There's my single hydrogen, meaning that I now have a carbocation. That's what happens. Meanwhile, if I have the blue arrow, then I have two hydrogens at this primary position, and if the electrons slosh toward the inside first before making a bond to the H, then what I end up making is a primary carbocation. I only have two hydrogens there. The new hydrogen is bound at this secondary position, so I now have two hydrogens internally, which means that I'm going to have a plus out there. This is a primary cation. This, of course, is a secondary cation. Which of these possibilities is allowed? Well, we cannot have a primary cation ever, which means don't ever show the formation of the primary cation. Instead, this is the only realistic option. So, I have shown you now once that you can slosh the electrons to one side or the other. I will never again draw the electrons that way. You should simply be aware that they can slide to one side or the other, and you must be deciding which way is the way to go. Again, primary cation will not be formed, so we need to make that go away. We're only going to make the more stable possible cation. This is, again, going to lead eventually to the Markovnikov product. The idea, again, is you will run this mechanism in such a way as to lead to the more stable intermediates, which leads to the only product observed when all is said and done. This way of drawing the arrows is silly, so I will cease and desist, but when you see this arrow here leading from this double bond, keep in mind that there are two possibilities you need to think about. The stable secondary Markovnikov product, Markovnikov in the sense that you make the more stable carbocation, which leads to the Markovnikov product, and the other one that I'm not drawing, which puts the cation at the primary position. It is fine when you are first practicing to draw both and then cross out the one and go only with the other. But eventually you should recognize you're always going to form the more stable possible carbocation. When we attack that H, now chloride minus will be floating around nearby. It will then add. It can add either from the top or the bottom of this carbocation site, which leads then, of course, to both potential enantiomers, the up chloride and the back chloride. So you get both enantiomers of this Markovnikov product. Keep in mind that these are both going to be equilibrium type steps. This, of course, can be eliminated. You can, with this secondary carbocation, run backwards to get to the elimination products. Both of these are equilibrium steps. And again, the point is that if your double bond attacks HCl, what you end up doing is adding H first and then Cl second. Since the H adds first, you form the secondary carbocation. Chloride attacks from top or bottom, making a racemic mixture, which is to say a 50-50 mix of enantiomers. And that is the general mechanism for hydrohalogenation. Reaction of a double bond with a hydrohalogen, HCl, HBr, and so on. This is how it works.